Welcome. In this video, we'll take a look at section 2.3, solving a right triangle. First, we'll take a look at some significant digit examples. Let's take a look at the definition first. We have the number of significant digits in a number is found by counting the number of digits from left to right, beginning from the first non-zero digit on the left. So, for example, if the number in question does not contain a decimal point, then the trailing zeros are not significant. So let's just take a look at a couple examples of numbers and identify their significant figures. So we'll take a look at first, the first number is going to be 0.042. So if I wanted to find the number of significant figures or digits for this number, I want to consider, again, counting the number of digits from the left to right, beginning with the first non-zero digit. So from left to right, the first non-zero digit is the 4, and then we have the 2. So this number is only going to have 2 significant figures. So this would have 2 significant figures. That would be the 4 and the 2. If I consider the number of significant figures in the next number, 20.5, well, the 2 would be significant. It's a non-zero number. The 0 in between the decimal point and 2, that would also be significant because we have a decimal point and another number after that. So that would be 0 and 5, all those would be significant. We would say that that has 3 significant figures, all of those 3. All right, let's take a look at the next one. The third number, we have 6.000. Now, we know that the 6 is non-zero, that's significant, and then we have a decimal and 3 zeros after it. So if I want to count from left to right the number of significant figures, we want to begin with, again, the first non-zero digit. And then we know that if the number in question has a decimal point here, these zeros after this decimal point will be significant. So zeros after the decimal point are significant. So these we would count as significant figures, each of those. So we are exact to the thousandth place here. So we'd have 4 significant figures there, all 4 of those digits. Now, this fourth number, 700, this is where we would differ with the zeros. So if the number does not contain the decimal point, then those trailing zeros we know are not significant, part of our definition here. So in this case, 700, this would be really rounded off to the nearest hundredth. And so those trailing zeros are not going to be significant. The only significant digit is the 7. And so we'd say we'd have 1 significant figure for 700. So when we don't have that decimal point there, we're really rounding off here to the nearest 100. So we have 2, 3, 4, and then 1 significant figure or digit in those numbers. Now let's consider how we would use significant figures in a triangle. So in terms of the accuracy of the sides and angles, these are the ways that we would want to round our value off to a specific significant value. So if our accuracy of sides is to 2 significant digits, then we would want to go to the nearest degree for our angle. If we have 3 significant figures for our side, we want to go to the nearest 10-minute or 1/10 of a degree, depending on which way we're going to write it. And if we have 4 significant figures, we'd want to go to the nearest minute or the 100th of degree for your angle accuracy. So let's take a look at the next example, and we'll take a look at these triangles and how we want to round the given sides or angles based on the other two figures. So if we take a look at problem A, we want to, for each of these triangles, round the number in the parenthesis so that its accuracy corresponds with the accuracy of the other numbers in the triangle. So we can consider these other two numbers. We have an angle to the nearest degree, and we have two significant figures for our side length. So that would really put us in kind of option number 1 here if we wanted to write that up. We're kind of in option number 1 or case number 1. So here we want to round again our other side length to two significant figures. If we wanted to do that, we would just have to round this to 0.9. That's one significant figure. And if we round the hundredths place, that would be a 4. That would make two significant figures. So 0.94. 0.94. The part B, we're also looking at a triangle. And we'll notice that this is rounded to the nearest tenth of a minute. And we have three significant figures for the 197. So we're really in, I think, option number 2 here. Three significant figures or digits for the side lengths. And so we'd want to round this off to three significant figures, which would make this 887 for that parentheses side length. The last triangle we have side lengths to four significant figures, both. Four significant figures. And so this would be in kind of option number 3. We would want to round our angle to the nearest minute or hundredth of a degree. So we're going to be rounding it to the hundredth of the degree because we have a decimal. And so if I round to the nearest hundredth here, we'd have 40.28 degrees. So that would be rounding that to the nearest hundredth, so it's accurate with those sides as well. Okay, so that was kind of just a little bit of a walk through how to work with our accuracy of sides and the accuracy of a given angle set. Let's take a look at a right triangle problem to finish off. So given the triangle below, we want to solve for the side length A and B and angle C and B. So we have 4 items to solve for, 2 side lengths and 2 angles. So let's consider looking at this triangle first, and we'll try to decipher what the angles are and find those side lengths through some trigonometry. So first, let's look at the angles. If I have a right angle in the bottom, C is a right angle or 90 degrees, I know that a triangle has to add up to 180 degrees. So when I consider these angles, A plus B plus C have to equal 180. And I already know C is 90 and A is 40. So I can say that 40 plus B plus 90 degrees is equal to 180 degrees. And I have one angle to solve for. 90 and 40 give me 130. So if I subtract the 130 on both sides, this will give us the angle B is equal to 180 minus 130, and so we've got 50 degrees for that angle. So we have 50 for that angle, and now we can work with our sides. So let's take a look at side A first. If I wanted to solve for side A, we can consider using one of our trigonometric functions. And for this, we'll just use the sine function. So if I take a look at the angle 40 degrees, that's the one that we started with, I know that the sine of this angle, that ratio would be my opposite, that's A, and the hypotenuse. So if we call this the opposite, this is the adjacent, and this is the hypotenuse. So when I look at 40 degrees, I can say that the sine of 40 degrees is equal to side A divided by hypotenuse of 12. Here I can rearrange this equation to solve for A, and we can say that 12 times the sine of 40 degrees is equal to A. If we put this into our calculator, we can go and solve for this. Notice that my side lengths are to 2 significant figures. We'll just do 2 significant figures on our side lengths. So if I consider that angle, or the side length A, make sure our calculator is in degrees when we plug this in, 12 times the sine of 40. So if we do 12 times the sine of 40, this will be approximately 7.7. If we want to stick with that same angle, we can use the cosine function to solve for our adjacent side B. So if we do the cosine of 40 degrees, that would be the adjacent side divided by the hypotenuse. So we'd have cosine of 40 is equal to B over 12, or 12 times the cosine of 40 degrees is equal to the B side. Again, we want to be in the degree mode in our calculator. We'll round this off to 2 significant figures. So B, side length, will end up being 9.2. So we have 9.2, and our opposite side was 7.7. So that completes this problem, but I want to point out a couple things that we want to think about when we're complete with a problem. One is to check if our side lengths match up with our angles. So notice that the hypotenuse is always going to be your largest side. That's across the largest angle, which happens to be 90. We also want to check that our opposite angle to our smallest side is the smallest angle. So if I consider 40 degrees, that's the smallest angle. And my opposite side, 7.7, is my smallest side. So in ratio, our triangle makes good logical sense. So those angles and opposite sides should have a ratio together. The smallest should correspond with the smallest angle, and the largest side should correspond with the largest angle. All right. So with that, we will hop to the next video. In our next video, we'll take a look at the applications with right triangles. I'll see you in the next video.